Hey, all right, I'm gonna put up a warm up here. Let's see. Hmm. Yeah, let's try this. So, yeah. Actually, hold on. How about nah, this is good for now. Okay. Um, so yeah, we'll say yeah, 5:15 as usual. Okay, so let's go over this. All right. So basically, these two series are just like special values of the general power series sum of n x to the n, right? So here, this would be where x is 1/2, and this is where x is like -1/3. And this has like, radius of convergence. Oops. 1. So, these both obviously converge. I mean, you can tell they converge just from like looking at them. But the point is that like you can get both of them by just evaluating this at the corresponding value of x, right? And then, so like we saw in the lecture, this you can obtain as like the derivative, or sort of a modified, like you can get it from taking the derivative of x to the n. So we have like the sum of just x to the n from n equals 0, let's say, to infinity. It is 1 over 1 minus x for x less than 1. So the sum of n x to the n minus 1 from n equals 1 to infinity is, 1 over 1 minus x squared by taking derivatives on both sides up here. This is also for absolute value of x less than 1. So then the sum of nx to the n is just x times this, right? So the sum of nx to the n from n equals 1 to infinity is x over 1 minus x squared. So this is going to be whatever you get by evaluating this at x equals 1/2. So you get like 1/2 over 1/2 squared. So it's like 2, I guess. Yeah, and then this one is -1/3 over 1 minus -1/3, so 4/3 squared, which is like -1 over 16 over 3. So -3/16, I guess. Is that what you guys got? Or do you disagree? Anyone disagree? I think this is right. 16 over 9. Yeah. So any questions about this? Yeah, so you can pretty much, yeah. Like I was saying in lecture, you can pretty much find formulas for, in fact, I think you can go even further and say like, there are formulas for like, oops. In general, I think you can do this, and all you have to do is sort of like build up Q of n by taking a bunch of, or like integrating a bunch, So what you do is like, let's say you factorize Q of n into a bunch of linear factors, then you multiply, if you need to, you can like multiply by some power of x to make the power, the exponent up here be like one of these factors of Q of n minus 1, and then integrate once, and then just like keep doing that over and over again. So keep multiplying by whatever power of x you need to multiply by, and just integrate repeatedly until you get Q of n at the bottom. And then you can differentiate a bunch by doing, you can do the same thing, like multiply by power of x, differentiate to get some factor, a linear factor of n up here, multiply by another power of x, differentiate again, and keep going. And then you'll end up with some closed form expression for this series. Obviously, it gets really complicated, like I was saying, when P and Q are complicated, but in principle, you could do it. Yeah. So, do you guys have any general questions so far? About, any of the material, including the material before the midterm? Okay. Yeah, as far as the midterm is concerned, by the way, yeah, I think I should be posting solutions sometime tonight. And then also, yeah, I'll make sure that the first homework gets posted like as soon as possible after discussion is over. Sorry, I'm a little bit behind on that. But I figured like no one was really going to be working on the homework immediately. So it's probably like not a huge deal, but it will definitely get posted tonight for sure. Okay. Okay, so let's see. What should we do next? How about this one? All right. So right. And okay. So prove S prime equals C, C prime equals negative S. Prove S squared plus C squared prime equals 0. And then prove that S squared plus C squared equals 1. So, right, you might recognize S and C are the Taylor series. S and C are the Taylor series of sine of x and cosine of x. So this is sine of x, and this is cosine of x. But the point of this problem is that you don't have to like know any of this. Like you don't even, I mean, honestly, you can take these as definitions of sine of x and cosine of x, and then you can prove all of this stuff just from these definitions, right? So don't use anything about sine of x and cosine of x, but that is kind of floating around in the background, that's like what these actually represent, and that's why all this stuff works out. Or from a certain perspective, you could say that's why this stuff works out, I guess. So yeah. Anyway, here I'll make a room for you guys to chat if you want, and yeah, let's come back at like 5:35. So. There we go. Oh, hold on. I have to like minimize the whiteboard for a sec. All right. So anyway, yep, see you in like 10 minutes. All right, so let's go over this now. So for the first part, it's not too difficult. So what you can do first, like, well, I don't know. I mean, you can kind of see, right? Like you can kind of just see from looking at it that it's going to work out, because if you just differentiate this, like you get 1 and then you get 3x squared over 3 factorial here, which obviously becomes x squared over 2 factorial because the 3 cancels out. And then here you get like 5x to the 4th over 5 factorial, which becomes x to the 4th over 4 factorial. So like term by term, you know, they line up. And honestly, like if you just wrote that, if this was some kind of a homework or an exam question and you just wrote that, I would pretty much just give full credit for that, because you know, it's like when you say something like that, it's very obvious that you like understand the pattern of what's happening, right? But if you want to see just, you know, what a slightly more formal proof of it might look like, you know, you can write down formulas. So we could write down like a formula, like an actual series with a formula for the coefficients that represents sine of x. So s of x is the sum from, let's say, k equals 0 to infinity of x to the 2k plus 1. Okay, so whenever I do like try to approach, you know, writing down a series like this, first of all, when I look at this, right, I notice that all the exponents are, like all the powers of x are odd, right? So, and then I kind of think, okay, you know, like what's a sequence that gives odd values? Something like 2k plus 1, right? That's always odd. And then the question is like, okay, where should k start? Well, the first value of k should make 2k plus 1 be 1. So k should start at 0, right? So that's kind of where we get this. And then the question is like, how do you relate like this index k to the coefficient here? Well, what we see is that it's always like, you know, it alternates. So it's positive here when k is 0, negative when k is 1, positive when k is 2. So it's something like negative 1 to the k, and that actually works out. So like negative 1 to the k when k is 0 is 1, right? And then when k is 1, you get negative 1. So I kind of like, I think it's good to get in the habit of just thinking through all the different pieces here, all the different patterns, and just trying to match them up to like an expression for the first few values of k. And then like things will just work out. So, and then it's always getting divided by some factorial, and the factorial is just always the same as the exponent of x, right? So that's why it should be 2k plus 1 factorial, okay? So this is sine of x, and then similarly, like cosine of x would be the sum from, let's say, k equals 1 to infinity of negative 1 to the k plus, let's say, k minus 1 over 2k factorial. Oh, actually, sorry. This one should go from k equals 0 to. So then this should be just k. And then this should be x to the 2k. Okay. Because the first term is 1, and then like 0 factorial is 1. So, okay, so now what happens if we differentiate sine of x, right? So s prime of x is now the sum from k equals 0. It's still k equals 0 because the very first term when k is 0 has a positive exponent. So it doesn't go away. It actually doesn't go away when you differentiate. So you get the sum from k equals 0 to infinity of negative 1 to the k. And then we'd have, you know, over 2k plus 1 factorial. And then we have 2k plus 1 x to the 2k, right? And then this 2k plus 1 just cancels with the 2k plus 1 down here to give you 2k factorial, right? And then you end up with this. And so that's just c of x, right? And then, oops, c prime of x is the series from, and now, so this one, when k is 0, you get a constant term, right? And so that just like goes away. So let's just start k at 1 here. And then you'd get x to the 2k minus 1. So you'd have like -1 to the k over 2k factorial. And then you have 2k times x to the 2k minus 1, which is the sum from k equals 1 to infinity of -1 to the k over, and then the 2k cancels here. So you have 2k minus 1 factorial x to the 2k minus 1. And then basically, now, since this one starts at 1, we have to like re-index it. If we want to compare it to s of x, right, the way it's written up here, we can re-index this by starting at k equals 0 instead. So k equals 0 to infinity. And then, so that means that originally the first value of k is 1. So this should be like k plus 1 now. So that way when k is 0, you still get a 1 up here, right? And the first value down here is 1. So it should be 2k plus 1 now, right? And you can just kind of check, like you can check that these line up with each other, right? So like when k is 0, you get 1 down here. When k is 1, you get 3. And when k is 1 over here, or when k is 2 over here, you get 3, right? When k is 3, you get 5. And when k is 2 down here, you get 5, right? So they just match up term by term. So that's how you can always like avoid making mistakes when you re-index, is just like write down what you think it is. And then if it's off at all, you can kind of like just shift it around until it works, basically. And then down here, we'd get like 2k plus 1 also. So notice now that there's like this extra, like it's k plus 1 now. So you can just factor out a -1 and get rid of the plus 1. And then that's negative s of x, right? Right. So that's the first part. Any questions about that? So technically speaking, you know, there's something floating around in the background about like, okay, so it's not hard to show that the domain of convergence for both s of x and c of x is all of R. Then like theorem, basically what, theorem like 26.5 tells us we can find s prime of x and c prime of x by differentiating term by term for any x in R. Okay. So, you know, yeah, it's really the fact that they converge everywhere. That's that, because they converge everywhere, then like, yeah. Well, I guess we're also kind of assuming, we're assuming that we know, and so we're also assuming that like s of x and c of x are known to be differentiable, which of course that's just like, because that's one of the hypotheses of 26.5. So without like a little bit more work, we're kind of just like relying on this assumption. But of course, that's like okay, because, you know, I mean, I'm not expecting you guys to like show somehow directly that like these are actually differentiable functions, you know. We're just going to leave that in the background, I guess. Okay. But given that we know all of these things, then we are actually allowed to like proceed this way. Okay. So that's kind of the point of this. And then, so for part B, right? Part B was show that, so s squared plus c squared prime is 0. So for this, you can just use like the sort of rules of differentiation, right? So this is, so s squared plus c squared prime is going to be, you know, s squared prime plus c squared prime, which is 2s s prime plus 2c c prime, right? And then by part A, this is, you know, 2s s prime, or sorry, so s prime is c plus 2s, and then c prime is negative s. So then these cancel out, which is 0, right? And then for c, since s squared plus c squared prime equals 0, we know, and this is on R, we know s squared plus c squared equals k for some, oops, right, that it's a constant function, right? So then to get k, so then like s of 0 squared plus c of 0 squared equals k. And s of 0 is 0. And c of 0 is 1. So this is k. So s squared plus c squared equals 1 on R. Okay. Any questions about that? Okay, so one thing I wanted to show you guys actually is, yeah, I think we probably don't have time for another problem. So one thing I wanted to show you is that, like, okay, so I think it's possible in this one, at least if you didn't do part B or part A, and you were just trying to show that like s squared plus c squared equals 1, right? If you're just trying to show this out of the blue, a lot of people, you know, myself included, honestly, I mean, if I was just like handed this problem or something, it would at least occur, the idea would occur to actually try to like square these series and then add them together and show that you literally just get 1 that way. And of course, that's like much less efficient. I mean, it's much more complicated than this method, but you could actually do that. I mean, it's not a terrible idea. And to be honest, like I actually think that the practice of like, you know, multiplying infinite power series together, like that's a good like that's a good sort of computation to practice doing, basically. So like what I want to do is show you how you can like do this. So at least you can kind of like, let's just look at like a few terms of what we get when we square these series, basically. Okay, so we would have like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus, I don't know, x to the 7th over 7th. Sorry. X to the 7th over 7 factorial, and so on. So here's how I think about doing this. And I really think that this is like a good thing to get used to being able to do. So we just go to calculate s squared. We just go term by term. We go degree by degree, and we collect together all of the possible ways of getting that degree in the product up here, right? So it's like, okay, is there a constant term, right? Because basically when you square this, right, when you square the series, when you distribute it, the result of like distributing the square of the series out is just that like you get a big series where every term is just a product of like one term in this series with a different term in the series, right? So it's kind of like if you imagine there being two copies of this, right? And like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus and so on, right? So there are two copies of this. To get every possible term from the that actually shows up in the product, all you have to do is like go through the ways of choosing one term from this factor and a different term from this factor and multiplying them together, right? So like, okay, there's no constant term down here because the smallest degree that you can get, right, would be if you chose x here and x here, right? So actually the smallest term, there's no linear term either, right? The smallest term is x squared. And there's only one way to get x squared, right? Because you have to pick x here and pick x here. If you pick any other term, you're going to get a higher power of x. So there's a 1 times x squared as the first term, right? Okay, and then like, okay, let's think about x, you know, okay, x cubed, it's impossible to get. One thing you can notice is that like all the powers are odd. So no matter what you're doing, whenever you multiply two of them together, you're going to get an even power of x because you're adding together two odd powers of x. So we only have to look at even powers of x when we do this. And so the next even power would be x to the 4th. And so there are two ways to get x to the 4th, right? You could take x here and negative x cubed over 3 factorial over here, or you could take negative x cubed over 3 factorial here and x over here, right? So that's, and either one of them comes with a minus sign. So there's going to be a minus 2 x cubed over 3 factorial, right? Or sorry, x to the, that's x to the 4th, right? And then plus, or no. Okay, so let's look at the next thing. So the next one would be x to the 6th, okay? So now there are actually like 3 ways to get x to the 6th, right? One of them is like x times x to the 5th over 5 factorial, or you could like flip that, right? So that's 2 ways. And then there's a third way, which is choosing the cubes from both, right? So we would get plus, so we'd get, there's a 1 over 5 factorial and a 1 over 5 factorial. So that's like 2 over 5 factorial, and then minus 1 over 3 factorial squared. And then this is all times x to the 6th, right? So all I'm doing, literally all I'm doing is like collecting like terms, right? And believe it or not, I mean, this looks really complicated, but believe it or not, you can actually come up with a formula. I mean, it's not that hard actually to write down a formula for this. And then you could actually compare it to what you get. I mean, we can actually compare this to what we get term by term for, wait, yeah, let's do, yeah, let's leave it at this for now. And then let's look at c squared. So that's like 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And then since, oh yeah, so we need x to the 6th over 6 factorial plus etc. And then 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, so on. So then this will be, so we get a, wait, hold on. Oh, right. We want 1. And then we want all the other terms to cancel out. Right. So we want a 1. And then, right, so again, we're only going to have even powers because we're always adding together two even numbers for the exponent. So for x squared, right, we're going to get like minus x squared over 2 factorial and also another minus x squared over 2 factorial. So that's minus 2 x squared over 2 factorial, which, as you can see, the 2 and the 2 factorial cancel out. So you end up with a minus x squared, right? And then for x to the 4th, there are 3 ways, right? So we can get, there's like 2 1 over 4 factorial. So that's 2 over 4 factorial. And then 1 over 2 factorial squared. So plus 1 over 2 factorial squared. And that comes with a positive sign because these are both negative, right? So this is now x to the 4th. And then one more would be, so for x to the 6th, there are 2, and then I think, so 4 ways, I think, because you can do 1 and x to the 6th, and then, or you can like flip that, or you can do like 2 and x squared and x to the 4th, or you can flip that. So here you could get like, for the 1 and x to the 6th, you get, so there are 2 negative 1 over 6 factorials. So negative 2 over 6 factorial plus, and then for the other one, it's going to be negative, so it's going to be like negative 2 over 2 factorial, 4 factorial. All right. So let's just like check that these actually cancel out. So we saw that this is going to cancel out with this, right? So this one, let's see what this is. So this is 2 over 24 plus 1 over 4, which is, so this is 1 over 12. And that's, so then this is like 3 over 12, so that's 4 over 12, which is 1/3. So this is 1/3. So this is 1/3. And this, right, is also negative 1/3, right? And then this one, let's see, this is like, okay, so we have like, so 5 factorial is 120. So 2 over 5 factorial is 1 over 60. And then minus, and then 3 factorial is 6. So this is 1 over 36, which is like, I don't want to think about that. This is like 6 times 10. This is 6 times 6. So, oh yeah. So this would be like, so you can multiply this by 6. So this is like 6 over 360 minus 10 over 360. So that's negative 4 over 360, which is like negative 2 over 180, which is negative 1 over 90, right? And then this is going to be, so we have negative 2 over, let's see, 720. So that's negative 1 over 360. And then this one is like minus 2 over, and then 2 factorial, 4 factorial. That's what, 48? It's 4 factorial is 24 times 2, yeah. So I don't know. This should work out to the same thing. I guess the question is this, oh, maybe I made an arithmetic mistake somewhere. This is like 1 over 24. Oh, wait, no, this should be plus. Sorry, wait. Yeah, right. Oh my God, okay. Yeah, because they were both negative before. So this is plus. So this is actually like, okay, right, good. Because they're supposed to cancel each other, of course. So this is like, right, 6 plus 10 over 360. So that's 16 over 360. So anyway, well, whatever. So this is 16 over 360. So if you don't make silly sign mistakes, it all should work out. So the question is this equal to like 15 over 360? And I think it is. Oh my god. All right. Anyway. Yeah. I think that's right. Yeah. So anyway, yep. That's all. You know, the reason. So the reason I think this is really useful, actually, it's again, it's like it might seem insane for me to say this given how complicated this is, right? But I genuinely think it's worth practicing, because the thing about this is that like when you think about things this way, it gives you a fast way to like mentally think about what the derivatives of like the product of two series might be, right? Because the thing is, the derivatives, right? The derivatives are related to the coefficients you get here, basically. So this is actually something that, like, I think in physics, like people do this all the time in physics, where they're like interested in like what is the first derivative or what is the second derivative of some function, evaluated at like 0 or something, or like how do you approximate a certain like function to like a certain order, so like first derivative or second order, like first order, second order, third order like approximations of functions when you like perturb their input by a small amount. And so for that, you basically use Taylor series, and it's like all you have to do is kind of collect together all of the like sort of first, second, or third order variations in either, if you're multiplying two functions together, you just have to sort of collect together the various like orders of variation that might happen, and sort of add together the ones that like sum up to a particular order of like the approximation that you're trying to find, basically. So you can use this to like mentally, you can kind of think about like low order behavior of the product of two functions somewhat efficiently. Obviously, you don't have to like, in this case, it was inefficient, but like in other situations, it's efficient to be able to do this, basically, is what I'm saying. So anyway, I think it's kind of cool to look at. I think it's cool that you can like even multiply infinite series like this in the first place, because it seems so complicated, but it's actually not as complicated as you think. So anyway, yeah, that's all for today. Like I said, I'll post the homework very soon, and I'll post the midterm solutions either tonight or tomorrow morning. And I have office hours tomorrow morning, and yep, that's all. So see you guys later.
Thanks.
Mm-hmm.